Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
So friends, what we have seen is how temperatures can be calculated within structural members, okay, and how these calculations are important and they form the basis for design against fire. Now, we will begin to talk about design of structures. So, first and foremost will be the design philosophy. Okay. As we all now predominantly use the limit state method of design, the design philosophy that we follow for limit state is that we define a design limit state function. Okay. So, it is generally a function of D and R, where D is the demand and R is the resistance. Okay. And generally for limit state, what we would require is that resistance should be greater or equal to the demand. When it becomes equal, we say the structure fails. So, this is the limit state. Now, when we are designing against fire conditions, we can talk about two conditions. One is the normal condition, which we normally do, which is the cold condition, which is if the fire is not there, then how the limit state is. And then there is a fire condition, which is hot conditions. So, we have one limit state which is applicable in general, but then the fire limit state function will be a function of R fire and D fire. where R fire will be the resistance during a fire and D fire will be the demand during a fire. Now one may ask or wonder whether the demand during a fire can be different from demand under normal circumstances. Okay. So usually this cold condition demand will be greater or equal to the fire condition demand. And the reason for it is that we again recall that normal time temperature graph, and we said that structural ratings or structural functions become important during the post flashover stage. So during the post flashover stage, when the system reaches the post flashover stage, by that time much of the combustibles within a compartment or a room, they would have already been consumed by the fire. So the overall live load of a building would reduce. Another reason for live load to reduce is that a lot of hopefully all the occupants of the building would have been evacuated by that time. Okay. So the live load reduces from that perspective also. So from this particular reason, international codes enable smaller load demands under fire conditions. Okay. So for example, from Eurocode, dead load demand is not changed, but live load, there is a permanent live load and a variable live load. So permanent live load, the load factor becomes 0.9, and for variable live load it becomes 0.5, which means things are getting consumed. Okay. And similar sort of logics and provisions are available in other codes. For example, in the American code or in the New Zealand and Australia code. Okay. So generally the demand during a fire will reduce. Okay. So what we are looking at for design under fire conditions, one is reduction in the load demand. Okay. Then second is additional stresses or strains due to thermal effects. We have already seen this, that due to increase in temperature, the thermal strains are introduced, and if a system is restrained, then it will lead to thermal stresses, which in turn can lead to failure. Okay, so these are the additional stresses or strains which are generated. We also saw that in case of non-uniform heating, thermal effects can cause additional curvature in beams or columns. The third effect is reduction in strength of materials. Okay. We have discussed this a little bit. We will see this in more detail today in this lecture, that strength of materials reduces, and we will see how it reduces. Okay. The fourth effect can be that the cross-sectional areas can reduce. For example, we saw that for concrete members, due to spalling, the cross-section may change over time during a fire event. Timber structures are especially vulnerable to cross-sectional changes. Okay. The other thing to keep in mind is that mode of failures also may change. Okay. So due to these thermal effects that we were discussing earlier, we may have thermally induced buckling or instability. Okay. A column which was not critical under buckling, under non-fire conditions, can have a buckling onset or an instability onset due to rise in temperature. Similarly, the location of plastic hinges may change because of moment redistribution. Okay. And obviously, there are many effects due to non-uniform heating. Thermal bowing can happen, additional thermal curvatures can come. Now let's look at some relevant codes that are there for design. So in India, we have this National Building Code. The part 4 deals with fire and life safety. Okay. IS 456 is the RCC design code, and IS 800 is the steel design code. Both of them include some provisions for fire resistant design, and we will discuss in the subsequent discussions. In USA, these are the codes. Australia, these are the codes. UK, these are the codes. So this I am showing just for reference, so that if you are intending to work with respect to any other countries' codes, this can be a starting point for you. Canada, these are the codes. New Zealand, these are the codes. And Euro codes, we have been using Euro codes quite a bit. So these are the general Euro codes. Okay, so the first Euro code gives design basis and actions. For RCC design, we refer to Euro code 2. For steel design, we refer to Euro code 3. Okay, there is also code on composite structures. There is a code on timber structures. There is a code on masonry structures, and there is a code on aluminum structures. So very comprehensive set of codes are available. Now, before we venture into design calculations, let us look at material properties, because we said material properties change, in fact they reduce as temperature increases. So first, for steel, we will see strength parameters. Okay. So generally, what are the strength parameters? They are basically derived from the stress and strain diagram of steel. We know that there is an initial linear period, then yielding happens, and then strain hardening comes in, there is an ultimate stress, and then finally failure happens. Okay. So the parameters of interest, one of them is E, the Young's modulus, okay, or it is also called slope of the linear elastic range, E. So if you look at this blue line, this is how Young's modulus changes with temperature. So on y-axis is a reduction factor. Okay, so we can say a reduction factor for Ke is the Young's modulus at temperature T divided by Young's modulus at some initial temperature T naught, which normally is 20 degrees Celsius. Okay, so we can say KET. So this is a reduction factor which is given here. So from here what we can say is that up to 100 degrees Celsius, okay, there is no change in Young's modulus. However, after that it begins to reduce. Okay. And what we see is at 500 degrees Celsius, it comes to 60% value, and somewhere between 500 and 600, it goes below 50%, okay, which means the Young's modulus becomes half of what it used to be. And we know that for steel, Young's modulus is about 200 gigapascals. So if we are in the temperature range of say 500 to 600 degrees Celsius, the Young's modulus becomes about 100 gigapascals. The other important parameter is this, which is proportional limit and yield stress. Okay, we look at the yield stress. So for yield stress, this orange graph is there. Okay, and again we can define a reduction factor KYT, which is a factor for yield stress, which is yield stress at a temperature T divided by yield stress at a temperature T naught, again typically room temperature or 20-25 degrees Celsius. And what we notice is that up to 400 degrees Celsius, there is no reduction in the yield stress. However, after 400 it drops very rapidly, so much so that again between the 500 and 600 range, okay, it drops by 50%. So this is the range where steel loses half of its strength. Okay, Fy becomes half of what it used to be at a room temperature. So these are the strength parameters. When we were doing calculations with respect to temperature, we were using three main properties. One is K, which is the thermal conductivity. One was C, which is the specific heat, and one is rho, which is the density. Okay. So generally, density doesn't change with temperature for steel. Okay, so it is considered to be constant. For K, the variation of conductivity with respect to temperature is shown in this figure. Okay. These are also available in building codes like Euro codes. So we see that at initial temperature, the conductivity is somewhere here, and up to 800 it consistently decreases. After 800 it is about constant, but for most fire calculations it is this up to 800 degree range which is required. Okay, and the drop is not very significant, but it is there. Okay, so it is somewhere 55 to somewhere below 30. So, roughly 1 by 2 factor. Then we talk about specific heat. Okay. So, this is the variation of specific heat with respect to temperature. The interesting thing is that there is a range here around 650, 660 degrees Celsius, okay, where there is a sharp peak in specific heat, which means that in this temperature, the heat storing capacity of steel increases substantially, but then again it comes back, and this is happening due to an internal grain restructuring. Okay. So, from a specific heat point of view, it would be generally okay to consider a constant value, all right, although it is more accurate to consider this value, but for practical purposes this may be okay, it does not involve too much of an error. Now, with these material properties in mind, let us go to design of steel structures. So, first we look at design of tension members. Okay. So, tension members, as we know, these are members which are subjected to tensile forces. So, there are two parts, one is the connection part, one is the section part. So, it can fail by say gross section yielding, net section rupture, or block shear failure. Okay. And generally the connections are most of the times protected. So, we worry more about the cross section yielding in this. Now, for cold conditions, which is the regular temperature design, the strength or the design strength is simply, or resistance is simply Fy times A cold. Okay. Fy stands for yield stress and A cold is the cross section area of the temperature. So, under fire conditions, we know that this Fy will get multiplied by a factor Kyt, okay, and this is the reduction factor Kyt. So, Fy reduces, other things remain the same. Okay. Now, although we have mentioned A fire here, which means we are enabling a consideration of change in cross section with respect to time or temperature, for steel members it is generally not the case. So, A fire and A cold are generally the same, and in such a case we can write the fire condition strength as simply Kyt multiplied by the cold condition strength. And this is because we said Ay is equal, A fire is equal to A cold, and the Ky variation is coming from this graph. Let us look at one example. So, there is an angle section of this size which is used as a tension member in a roof truss. Okay. We want to calculate its design strength in gross section yielding, okay, under cold conditions. That is the first thing. This anyway is done. Then if the member is subjected to a standard fire on all four sides, which means four-sided exposure, calculate its temperature and strength as a function of time. Okay. So, the temperature calculations we have already seen, and again I have included it in the form of the similar kind of codes that we have been seeing earlier. Okay. So, these are the section properties, this is the material data. See, C rho we have all considered to be constant. We have not assumed any time dependence as of now or temperature dependence as of now. So, C is constant and at 460 joule per kg Kelvin. Right. Now, this is the initial temperature. Again, recall that we are using temperatures in Kelvin because we want to consider the radiation boundary condition. This is the gas temperature, which is again 273 plus this is the initial ambient temperature and this is the ISO 834. This is the 834 relation. The method of temperature calculation is exactly the same that we were seeing in the previous lecture. After we have done the temperature calculation, then we can do the strength calculation. Okay. So, for strength calculation, what we require is Kyt. And for Kyt, you may recall that we had a graph of this kind, right, where this change was happening at 400 degrees Celsius, temperature KYT. Okay. Now this data at different points can be stored as a table, and given a temperature you can use linear interpolation to calculate KY. So that is what is being done internally. Once we know KY, we can then first calculate the P cold, which is Fy times the area. Okay, so here we are using the term V for area of cross section. Okay, so the area of cross section is known, Fy is known, so we can calculate P cold. Okay. Now you may also notice that there will be a material factor gamma m naught with which this Fy has to be reduced or divided. Okay, but I am not showing that here because that is understood and we are focusing more on the fire side. The P hot can simply be calculated as using this relation, okay, Ky times P cold. Okay, so this is all that is required for calculation. So we do this calculation, then we can plot the time versus temperature as well as the strength versus time. Okay. So here what we see is the graph on the left is the temperature graph. So this blue curve is the ISO 834 gas temperature. Orange curve is the structural member temperature. This we have done earlier also. But now we get a strength in kilonewton, which is the P fire, P hot or N fire versus time in minutes. Okay. And we see how rapidly this strength drops. All right. So in this case, since we have not defined any demand, so let us say that demand on this member was 150 kilonewtons. Okay, so if demand was 150 kilonewtons, we see that the time it takes is say about 4 minutes to fail. Okay, and since we are doing this simulation with respect to the standard fire curve, from here we can conclude that the fire rating or the strength fire rating of this member is 4 minutes. You will notice that these ratings are very small because unprotected steel members, because steel is a good conductor of heat, can achieve very high temperatures in almost no time, and because the strength drops significantly after 400 degrees. Okay, so you will see that somewhere here. Okay, so as soon as we go above 400, the Ky becomes very less rapidly, and when we reach about this, then the strength becomes half of it. Okay, so for that reason the fire rating of unprotected steel members is very small. This is where protection is always required. Now in the previous example, we considered the specific heat to be constant. Okay. However, we saw that the variation of specific heat with temperature is like this, where there is a region here where the specific heat is very high, which means heat capacity becomes larger during this temperature. So let us look at an example where we do consider this temperature dependence. Okay. So an IS LB 250 is subjected to an ISO fire, and we have to calculate temperature as well as strength with respect to time. Okay, so temperature calculations are like this. The only change that would happen is in this. Okay, so in C, now we have considered the specific heat as a function of temperature. Basically, again, this data is what is obtained by here. Okay, using this, we do temperature calculations, and then strength calculations remain the same. Okay, so we calculate Ky. So P cold is Fy times V, and P hot is Ky times P cold. Okay, and then we do the plots. These are the relations that we have been working with. Now, when we do the plots, you will notice that the time temperature relation, the structural time temperature has a sort of a kink here. Okay, this is happening because this is that time zone, temperature zone. Okay, when the specific heat becomes large, and when specific heat becomes large, it begins to absorb more heat, and hence the temperature rise becomes lower. Okay, so that is the small dip here that is observed, and the same dip corresponds to the strength also. Okay, however, again, if we say that, say, demand was, say, 500, right? So for 500 demand, the rating is about 5 minutes, right? So again, structural rating is very small because steel is a good conductor of heat. It absorbs, or the temperature rises very rapidly, and beyond 400 degrees, the yield strength drops very rapidly. Before we move further to, say, consideration of beams, let us discuss something called shadow effect. Okay. So imagine there is a floor which is being supported on an I beam like this. Okay. And in this room, there is a fire which has happened somewhere here. So the direct line of path, if we see, which is relevant for radiation, which in a way dominates the heat transfer process. Okay, so the direct path to the member is like this. So when we look at this, what we will notice is that this part of the structural member, and maybe some part like this is shadowed from this fire by the member itself. Okay, so this perimeter of the member is not getting any radiative heat flux. It is only getting convective heat flux because of the hot gases. So this has to be taken care of in the heat flux that we use in the temperature update condition for the lumped capacity model that we were using. Okay. So one possibility is to again go into the full details, but then after doing a lot of such calculations, a simple shadow factor has been defined. Okay. So shadow factor defined as 0.9 times this perimeter, which is the boxed perimeter of the beam. So this is the boxed perimeter divided by the actual, So now it is easy to see that when KSH is equal to 1, okay, it implies that we are not considering shadow effect. So no shadow effect. And this will be on the conservative side. Why conservative? Because of the shadow effect, the rate of rise of temperature will be smaller compared to the case when we do not consider any shadow effect. Okay, because this green boundary here, this is protected from direct radiation exposure. Okay, so radiation requires a line of sight for the flux to reach. Okay, so now with this, let's look at design of flexural members. Okay, so we can divide the design of flexural members into two parts. One is when lateral torsional buckling is not critical, which is the case for laterally restrained beams. Okay, these can achieve full plastic capacity. In such a case, M cold is simply Fy times Zp, Zp being the plastic modulus. And since the temperature dependence is coming from Fy only, okay, M fire can again be written as Ky times M cold. This is similar to what we were writing for tension members, except that for tension members we were writing it for N fire equal to Ky times N cold. Here we are writing for the moment, which is M fire equals to Ky times M cold. Now when lateral torsional buckling is possible, okay, then we can extend similar kind of principle for design. So let us say if we take IS 800 method for design. So for beams which are susceptible to lateral torsional buckling, the moment capacity is written as beta B times Zp times FBD. Okay. Zp is again section modulus. Beta B is given here. So depending on the section classification, so if it is Ze by Zp, but for plastic and compact sections which can achieve full plastic moment capacity, this factor will be not there, it is 1. Okay. FBD is this stress. Okay. So it is defined as this reduction factor multiplied by Fy by gamma m naught, right. And the reduction factor, it is linked to account for the lateral torsional buckling, which is given here. Okay. It includes this alpha, which is an empirical parameter, and it also includes lambda, which is the non-dimensional factor for lateral torsional buckling. So as again this is here, okay, we see that this FBD has Fy. Okay. So this is one of the things that will change. So this will, we can say FBD fire will be phi LT times Fy by gamma m naught into Ky. Okay. So Fy gets multiplied by Ky. In a similar way, we can define equivalent fire versions for this reduction factor, and this in turn depends on phi LT and lambda LT. Okay, so phi LT has this form. So for this also there is a fire related version. Okay, and here the dependence is basically coming from lambda. Okay, and lambda LT is defined like so, like this. So a fire version can be defined like this, where this Fy gets multiplied by K, and the critical buckling stress also becomes a function of temperature, because the critical buckling stress has this E coming here, which becomes dependent on temperature. Okay, so then we can define this critical moment for lateral torsional buckling. Okay, here the shear modulus has been multiplied by Kg. Okay, so just like for E, we are using a reduction factor Ke. For G, we are using a reduction factor Kg, which can be derived using this. Okay, because there is a relation between E, G, and nu, which is Young's modulus, shear modulus, and Poisson ratio. Okay, so by introducing these strength and Young's modulus reduction factors, we can formulate an equivalent way of design using the basic design equations. So now let us look at an example. So we are asked that what will be the fire rating for an unprotected steel beam built using ISMB 350, where moment demand is given as 150 kilonewton meter. Now this again is similar kind of code that we have been seeing. Okay. This is gas temperature and temperature calculations. Now henceforth we will be considering the temperature dependence of C, which is the specific heat. So up to here is temperature calculations. Then we find out Ky, which is the steel strength reduction factor. Okay. Now since this is a beam which can become plastic, there is no lateral torsion buckling case which has been given in this. So we are simply calculating first the cold moment capacity, which is Zp times Fy divided by the material factor, and then m hot is simply Ky times that. Okay. This is what we have seen earlier. When we plot, the first plot is between temperature and time, and again you will see that this kind of kink will now be always visible, because we are considering the specific heat as a function of temperature, and this is the temperature zone where that kink happens in the specific heat. And then we plot moment versus time, moment capacity versus time. Okay, so the demand is here 150 kilonewton meter, So the demand is 150 kilonewton meter, and the moment capacity begins to reduce and it crosses the demand at this point. So from here we can say that the fire rating of this beam is 6 minutes. Now, as we have been discussing, that all steel members are generally provided with fire protection. So let us redo the previous example where the beam was unprotected. Using a protection now, a 30 millimeter fiber board protection has been given, which means for the I section all around there is a 30 millimeter board protection. Okay, so here we define insulation property. This is for the fiber board. Okay, so conductivity and thickness has been defined so that we can eventually define R, which is the thermal resistivity of this fiber board. Okay, and that thermal resistivity can eventually be used for temperature calculations. So this is the basic data. We have seen this kind of things earlier. Now this is where R in is used. This also we have seen earlier when we were discussing temperature calculations. Okay, so up to here we have done the temperature calculations, and once the temperature calculations have been done, the strength calculations do not change. Okay, strength calculations only depend on temperature through the factor Ky in this case, and if there is lateral torsional buckling also in picture, then Ke in that case. So now we plot. Okay, so we compare this plot with the one earlier. So this is unprotected. We will see that unprotected 15 minutes temperature is around 500 degrees Celsius, whereas in protected same temperature is reached around 55 minutes. Okay, so a substantial increase. Similarly, we plot moment capacity. Now the demand again is 150. So what we can see here is the fire rating is say roughly 24 minutes. Okay, so from 6 minutes it has gone up to 24 minutes by adding this 30 millimeter board protection. Okay. With this, now let us move on to design of compression members. Okay, so compression members can fail by crushing or by buckling. These are generally the two modes of failure. Again, we can define the, in case of crushing, this is the critical stress. Okay, in case of buckling, this is the critical stress, where the critical stress for cold here is coming from the Euler's buckling formula, pi squared EI divided by L effective squared. Okay, and this P fire, which is the actual load carrying capacity, that can be simply written as this multiplied by these two. Okay, where this factor chi is based on the buckling class. Here we have already converted them to the fire versions, which means that we started from the cold condition versions. Okay, where here if you see this lambda has the slenderness ratio, this has E. So instead of E we are writing Ke times E. Okay, where Ke brings in the temperature dependence of Young's modulus. Instead of Fy we are writing Ky times Fy. This brings in the temperature dependence in Fy. So this is the temperature dependent slenderness ratio. Okay, similarly we define this phi from here because it depends on lambda. Okay, so like this we are able to convert the cold condition equations to fire condition equations. So let us do an example of a compression member. So a column having an effective length of 4 meter is designed for a factored load of 1500 kilonewton. This is the demand using ISMB 450. So we calculate its fire rating if it is subjected to standard fire without any fire protection. So this part we have seen now multiple times, so I would not go into the details. This is basically all temperature calculations. Okay. And after temperature calculations are done, we can go to the strength calculations. In this case, we will need Ky and Ke both, which are the strength reduction factor and the modulus reduction factors as a function of temperature. Okay. Then we calculate the required quantity. So lambda fire is here, okay. Phi fire is here, and then high is here. Okay. So whatever these expressions are, using that we code that up, and then we calculate the hot capacity, which is this times area times Ky times Fy. And as earlier, we plot two things. One is temperature versus time, and one is load capacity versus time. Okay. And you will continue to notice this kink here. This is happening again because of the specific heat being considered as a function of time, temperature, instead of being constant. Okay. Now for this particular case, the demand is 1500 kilonewton, and that demand is crossed again around 7-minute time frame. Okay. So we see that the fire rating of this column without any protection is 7 minutes. As earlier, let us repeat the example, but with a fire protection of 30 mm fireboard. Right. So again, we will define insulation properties as earlier, which is for the fiber board. Okay. We use these properties to calculate the rise in temperature. So the rise in temperature will be more gradual, all right, as opposed to the unprotected case. This one shows the structural calculations. So again, we have already calculated the rise in temperature. So this part basically doesn't change at all. Okay. So Ky and Ke dependence is brought in using the appropriate functions. Then lambda fire, phi fire is calculated, and then P hot calculated in the same way as earlier. Now let us look at the temperature and strength. Okay. So we compare this temperature again with the previous one. So here we notice that at 60 minutes, the steel temperature is around 500 degrees, whereas in the previous case, at 30 minutes itself, it had reached almost 800, right? So this is the effect of fire protection. Okay. And because this temperature rise has slowed down, the strength reduction has also become more gradual. Okay. So in this case, can you find out what is the fire rating? Okay. So the demand is here 1500 kilonewtons. What will be the fire rating? It is the time at which the resistance, so this is the resistance, okay, resistance or the capacity, when it crosses or comes below the demand, that is the fire rating. So in this case, fire rating is about 20 minutes. So now from 7 minutes, which was earlier, it has gone up to 20 minutes. So this is the effect of adding insulation. Now when we are designing structures, we will look at this problem in reverse, which means we will be we require a 60-minute rating. Okay. So we require a 60-minute rating. We need to find out the amount of protection. So we need to design the protection for a given rating. So then what can be done is, just like here we have used a 30 mm board, let's say, and it is crossing at 20 minutes, okay, we can increase it till the time this crossover happens at 60 minutes. So that will be a trial and error process in general, but the idea remains the same, that we do same set of calculations, but we are now looking at it in reverse rather than in forward. Okay. So we require a 60-minute rating. We keep on increasing the thickness of the board until this crossing happens at 60 minutes. Okay. There are some empirical relations available for the amount of protection required for specific cases. okay, and some codes also provide that. However, that we are not discussing because we are more interested in the fundamental way of calculation. Now that we know about the method of calculations, let us look at some provisions of IS 800-2007 which are already there in our Indian code for fire resistance design. Okay. So, the section 16 of the code gives the requirements for fire resistance design. So, there are some terms which are defined in this. So, the basic terminology is like this, that the requirements shall apply to steel building elements designed to exhibit the required fire resistance level. So, FRL, fire resistance level, as per the relevant specifications. Okay. Now, for protected steel members and connections, thickness of protection material, okay, we have been discussing this thickness of the protection material, shall be greater than or equal to that required to give a period of structural adequacy. This is one more term, period of structural adequacy. Okay. So, this period of structural adequacy, this is like the fire rating. So, whatever is the fire rating required, okay, the fire rating is always measured in time units. Now, for unprotected steel members, the unexposed surface area to mass ratio, okay, this is like the section factor, shall be less than or equal to that. So, basically it is saying the same thing. So, whatever is the limit state, it has to be satisfied. Okay. Now, how do we determine PSA, which is period of structural adequacy? So, there is this clause given on that. So, the code enables a few methods of design or calculation of PSA. What we have learnt is here. Okay. So, this is by calculation of the temperature of the steel member by using a rational method of analysis confirmed by test data or methods available in specialist literature. So, the methods we have learnt for calculation of temperature and strength, these have been corroborated from experimental data for a long time, and these are also available in several building codes including Euro codes. Okay. So, the method of calculation we have used so far falls in this category. The other possibility as per IS 800 is by direct application of a single test, which means we take the structural member along with its fire protection and do a test. Okay. So, the method of test and how to test is also defined. The third is by calculation. This calculation is given in IS 800 itself. So, there is a calculation given for limiting temperature, we will see that shortly. Okay. And then from there you determine the PSA time in minutes. For advanced calculations where we require material properties, the variation of mechanical properties of steel with temperature is also given in the IS 800. Okay. So, this is figure 24 which shows variation of material properties. So, curve 1 is the yield stress ratio, okay, and curve 2 is the modulus of elasticity ratio. So, this is somewhat different than what we considered. Okay. However, most of these curves are of similar in nature. So, the curve that we have used in the calculations so far, these are given in the Euro codes. Okay. So, they are also code based, this is also code based. When you do actual testing and data collection, then obviously there will be some variations from what we have been considering. Just like we were doing earlier, this also defines KYT, which is yield stress at a temperature T divided by yield stress at 20 degrees Celsius. Okay. So, it gives a relation, so it can be used. Similarly, there is a KET which is defined, E at temperature T divided by E at 20 degrees Celsius. It gives a closed form relation which can be used. So, what we were using was using the curve we had tabulated, and from there we were doing linear interpolation, but it is also possible to use these relations. Okay. So, you can go back and change your code to incorporate these relations, so that when you are doing design with respect to Indian standards, this can be directly taken in. Then limiting steel temperature is what was discussed. Okay. It is mentioned in the calculation of the performance level. So, the limiting steel temperature which is given here, okay, is a function of basically it only depends on RF, which is the ratio of design action on the member to the fire resistance, right. So now let us say if we go back to the example that we did earlier, okay. So in that example of the column that we did, so we had P demand was 1500 kilonewtons, okay, and the P resistance or the capacity was 2350 kilonewtons, and this is the cold capacity, okay. So here also you will see that this design strength and ultimate strength of the member at room temperature, okay. So this is the cold condition things that we use. So from here we can calculate RF, the ratio, okay, so which comes out to 1500 divided by 2350, which is 0.64, and we put this RF here. From there we get a limiting temperature, okay, which is 905 minus 690 multiplied by 0.64, okay. So this limiting temperature comes out to 456.5 degrees Celsius. So this limiting temperature is what we have calculated. Now let's look at the time temperature graph that we calculated earlier. So if limiting temperature is around 450, 456, so this is the limiting temperature, okay. So from here we can infer what is the fire rating, right. So this fire rating is coming out to approximately say 12 minutes. You will see that this fire rating is greater than what we calculated earlier, okay. So strength based calculations are, I would say, more accurate because these relations are very empirical in nature, and using this TL, it defines a time of exposure. So this is the fire rating as can be calculated from IS 800, okay. So we have already calculated TL, which was 456 degrees Celsius, okay, and T is the actual steel temperature, and KSM is this exposed surface area to mass ratio, very similar to the section factor but somewhat different in this, it has different units, okay. So using all of that one can calculate the fire resistance as per IS 800, and as we have seen this limiting temperature was somewhere here and the actual rating was somewhere here. So there is some mismatch, and this is expected because the formula that is given here, whether it is for TL or whether it is for this, okay, this is a generic formula. It can be applied to tension members also, compression members also, bending members also as per this code. However, these members would behave differently under different conditions. Now we can look at the other example also for the beam, where we had M demand as 150 kilonewton meter, okay, and M resistance was 190 kilonewton meter, okay. So this RF, which is 150 divided by 190, this comes out to 0.79, and this RF to put here, so the limiting temperature comes out to 360 degrees Celsius, okay. So for this limiting temperature, which is 360, okay, so the fire rating would come out close to 8 minutes. So what we can notice is that in this case the fire rating is closer to the calculated fire rating, okay, that was around 6-7 minutes. So this particular approach or formula this has an advantage in the fact that it is very simple to use. Okay. But the disadvantage can be that depending on the member type and depending on the RF ratio, the results may be on the conservative side, the results may be on the non-conservative side. It depends on the calculations. In addition to this calculation method, IS 800 also gives two tables, table 31 and table 32, okay, which gives minimum dimensions of protection, fire protection of different steel members. Okay, so encased steel columns of this dimension. When protection is applied on all four sides, for such a dimension, it is possible to calculate, not calculate, it is possible to find out the required thickness for the required hour of fire rating. Okay. So, here if we want say 2-hour fire rating of column of this size, and we are using this gypsum plaster as a fire protection, for 2-hour fire rating we need 20 millimeter of the thickness. Okay. Similarly, there is this table 31. Okay, this is this is a larger view of the table, where you will see that there is a provision of plaster board using bricks of clay, asbestos, etc. So, for different fire protection and for different requirements of fire resistance, one can find out what is the required millimeter of thickness of the particular protection. However, as we discussed, this kind of an approach also suffers from the similar limitations as earlier, that in this case there is no dependence on the level of load. Okay. So, if under the cold conditions the capacity is very close to the demand, then under fire conditions such members will fail faster. Whereas, if there is a large amount of demand available, capacity available, then such members may fail much later in fire. Okay. So, this is where calculations of temperature and strength that we have been doing, those are very important. So, to summarize what we discussed in this lecture, one was the design philosophy and the limit states, and we saw how the demand reduction factors, demand reduces because of the difference in load factors. Okay. We discussed material properties of steel under high temperatures. Then we discussed design of steel structures using detailed calculation methods for tension members, flexural members and compression members. And similar to the temperature analysis approach, we developed some computer codes which can be directly utilized for design. Okay. And finally, we discussed some provisions of IS 800-2007 for fire resistant design. We saw that there are some empirical calculation approaches available, and a couple of tables are also given which can be utilized for directly finding out the required thickness for protection. So, overall what can be said is that for steel structures, unprotected steel structures have extremely small fire rating and are never to be used in any significant structure. So, wherever there is a fire risk, steel members of structural system must be protected with fire protection, and fire protection design can be done using the calculation methods that we have covered in this lecture.